Okay, so this is another fall 2015 exam. You guys do have the solutions for this. I'm just going to talk through the process. Again, we'll figure out it's an indeterminate. Indeterminate. Well, whatever. This time, instead of torque, we are looking at normal stress. Okay, we can see it's not a torque application. It is a axial normal stress. So we are going to set this up very much the same way. We are going to go ahead and find the area. So this is going to be 10 by 10. So our area is 100 inches squared. Over here, we have an area of 12 by 12. So we have 144 inches squared. We are told it is an aluminum bar. We'll get those values for you. But again, on the exam tonight, we will have all of the values you need on each problem. So when we are looking at this, then from A to B, determine at B the maximum. The aluminum AB is heated, so we're going to need to know its thermal coefficient, which is 12.8 times 10 to the negative 6 per degree Fahrenheit. Okay, and we need to know that its E this time is 10,000 KSI. And then we need to look at the other material, and we need to find what its E value is, and it looks like it is 29,000 KSI. So remember, this time we're using E because we're looking at normal stress. Okay, and we don't need the alpha of this material because we're only heating up A to B. So we are always going to start with statics, okay, with equilibrium. And when I look at this with equilibrium, I have an applied axial of 8,500 kips, which means I'm going to have a force here at the wall, force BC, and we're going to have a force over here, force AB. So I can sum the forces in the x direction equals 0, and I will find that force AB plus force BC equals 8,500 kips. Now, unlike the torsion problem that's on the same test, the torsion problem said, please make the torques at the wall the same so that you can calculate a diameter. This time, we have all of the geometry that we need, but we want to figure out what the actual force at the wall is. How is this 8,500 distributed? So we can see that it's indeterminate. We cannot determine the answer through statics alone. So now we have to go to compatibility. And again, with compatibility, I know that the change in length at B, so as AB gets longer, BC gets shorter, that delta has to be the same. Delta equals delta. Okay, and remember, delta is PL over AE. We are also assuming that we are staying in the elastic region. When we use these equations, our assumption is we're functioning completely elastic, which is in this part of our stress strain curve. Okay, so when we're looking at A to B, we are going to have both an internal force and we're going to have a change in temperature. Here we just have that internal force, and we're calling that internal force force BC. We're calling this force AB. So let's go ahead and get started. Let's start with our AB side. So I know that when I have this reaction at the wall, anywhere I cut, it's going to be internal the same, which is how I can go back and find stress if I want to. So when I'm looking at P, I'm going to have the force of AB, okay, times the length, 2 feet, and here we want everything to be in inches. So we could go ahead and change that to 24 inches, and we could go ahead and change this to 12 inches, and that way we can make sure that we are in constant units. Otherwise, you need to multiply by 12. So we have 24 inches. And then on the bottom, we have area. So we have 144 inches squared. We have an E, which is 10,000 KSI. So note K, we are going to be finding the answer in kips, which is what we're starting with this load. If this were in pounds, we would need to make sure we converted this to kips because our modulus of elasticity is in kips. Units. Units will get you every time. Check your units, okay? So that is my delta. And then in addition to that delta, we can see this is going to be getting larger. So that temperature change is going to add to it. And remember, delta T, so that's alpha delta TL. Our alpha is 12.8 times 10 to the negative 6 per degree Fahrenheit. Okay, our change in temperature, we are going from 50 to 160. 160 degrees minus 50 degrees. Okay, that's delta T. And then our length again is 24 inches. Please, please, please be in consistent units. Okay, so this is the left half of that system above equals, now we're going to go to the right half where we're looking at the force from B to C. We are also not heating over here, so we will not be including, we will not be having to include that temperature change. So let's look, we have the force from B to C. Okay, we don't know that. We do know the length is 12 inches. We have an area of 100 inches squared. We have a modulus of elasticity of 29,000 KSI. And that's all we have going on. And again, we can use these equations because we are assuming that we are linearly elastic, okay? Which is something we always have to check. But before we can find stress or deformation, we have to find those internal forces. So now I can see that I have an equation here, which is my statics equation, where I have an unknown force AB and force BC. And now we have our compatibility of deformation equation, where again, our unknown forces are A, B, and BC. So by the trick of videotaping, we are going to just get the solution. I hope you guys can all do algebra. And I am going to find that the force in AB is 66.38 kips, and the force in BC is 8433.62 kips. If I wanted to at this point, I should be able to add those, and indeed, they come up to the given of 8,500 kips. So that's how I can check to make sure my math is correct, because the force that's going to the left and the force that's going to the right should equal that original given. So here is a checkpoint that I can say, okay, I did something correct. I did my math correct because I indeed got 8,500 kips, which was my given. So the next thing we need to do is we need to check internal stress. Because again, we are assuming linear elastic behavior. So the stress of A to B equals the force of A to B over the length. So we have 66 over 24 inches. And then we can check the stress of B to C, which is the force of B to C over the length. And we have 8,433 over 12 inches. Okay. So as we're checking, we can find that this gives us 0.46 KSI. I'm going to assume that that is definitely below the yield stress. So this checks okay. When I calculate this, I get 84. Oh, why am I putting links? This is where I need you guys to say, hey, stress. Stress is force over area. Sorry, you guys know me, and I don't know how to edit, so I can't go back and fix this. Okay, so my area here is 144. My area here is 100. Okay, I do apologize. I really do. Stress equals P over A. I should have written out my equations because I get completely sidetracked. Stress, P over A. Okay, so my area here is 100, so I'm going to get 84.3 KSI. Okay, and that is much greater than our yield stress of 36 KSI. So it yields. So this goes back to, I'm going to turn a piece of paper over here. This goes back to the tug of war, okay? Our whole system doesn't necessarily have to fail because I can be on a tug of war team with a friend, and if I slip and fall, okay, my friend is going to have to pick up my slack because we don't want to fail the tug of war. We don't want the other team to win. We don't want that little flag to cross the mud line or the painted line or whatever. So if I slip and fall, my friend over here, AB, has to carry the slack so that we don't have a complete system failure. So that's where we're going to get started now. We found that we yielded. So we don't want to yield. We don't want to yield. We don't want to fail. So I know when I'm looking at steel that my yield stress is 36 KSI. So that's all I'm going to be able to take. Okay, so now we get to back work this problem. So if the most I can take is 36 KSI and stress equals P over A, I have 36 KSI equals that force in BC over 100, and the force in BC is going to be 3,600 kips. Okay, that's the most that we can take before we enter the non-elastic region. So if the most we can take is 3,600 kips, then we're going to keep looking back at equilibrium, and we are going to find that the force in A to B, okay, has to be the total that we've applied to the system, which is 8,500 kips, minus the most that force BC can take, that's the max, and we get a new force in A to B of 4,900 kips. Okay, so once again, the 4,900 plus the 3,600 equals 8,500. We should check yielding again. Is the yield stress, okay, is that greater than the actual stress from A to B, which is 4,900 kips over 12? 12 squared over 144, okay? If this still holds true, check. We are still in the elastic zone in A to B, okay? So now if I want to check deformation, okay? If my deformation equation is a function of my assumption that we are linearly elastic, then can you use the yield stress that we're getting in BC, or should we use the region that has linear behavior? Okay, you guessed right, the section with linear behavior. So I know that that delta is going to be a function of both the applied load, which is the reaction at the wall, and that change in temperature. So I can find delta of A to B equals 4,900 kips times 24 inches divided by PL over A, 144 inches squared, times, I think it was 10,000 KSI, plus we have that alpha. I have to go back and look at my paper because I don't have anything printed out useful. 12.8, so we have 12.8 times 10 to the negative 6, okay? Our delta T is still going to be that original delta T that we had, which was 110 degree difference. And then our length is still 24 inches. So when we calculate delta from A to B, we are going to get 0.115 inches. It is positive, so it's moving to the left. This is going to be the delta at B. So when I go back and look at the overall system and I apply this load, if I'm looking at point B is going to shift over 0.115 inches. Okay, so we've remained in the linear elastic region here. We've maxed out here, and we are going to transfer. That's what we did, is we just transferred some of that load so that we don't have complete, like, beyond yielding behavior. So again, this is a problem you could work forwards and backwards. I could have said, if I want the reactions at the wall to be the same, what diameter part do I need over here if I had two materials? This is how I would approach it if I had two materials also. These were two materials. I'm sorry. I'm really tired. But you could do the same thing where we went back and found geometry, just like we did on that torque problem. So I hope you guys understood, and I will see what I can do about getting more up.